Okay, so this talk is basically going to be sort of about what Dave and I have been doing for the last, 5 or 6 years, and hope to continue doing for the next N years. And it's, it's in part sort of a we're not dead yet kind of talk, feeling better all the time. So, all right, so just to give you some background, because I suspect Standard ML of New Jersey is actually older than some of the people in the audience. This is a system that dates back to the March 86. Okay, so dates back to the over 35 years ago, and it is was originally designed around the traditional functional REPL type model of interaction, and a lot of people's introduction to it is through the REPL, but it's not an interpreter. We frequently get email messages about the interpreter, but there's no interpreter. It's actually from the very beginning, it was native code generation on the fly, and also then a batch compiler that produces files with the native code in it. And one of the early original design philosophies, I don't know if this was ever stated explicitly, but it can sort of be reverse engineered from the implementation, was that the system should be self-contained and self-supporting. So minimal dependencies on the outside world. So in particular, the only external dependencies were really, you had to have a C compiler, you have to have a shell, Unix or DOS, and you have to have make, or on Windows, nmake. And if you had those things, you could basically build the system and run it. So this philosophy meant that, of course, things like Yak, Lex, build tools, all of that stuff had to be written for the system. And so there's a lot of that, tools and libraries, and they're all, largely that code is all written in standard ML. And that was, in some respects, that was a sort of a good demonstration that you could build these, a reasonably large and robust production functional language implementation, and it would actually work. But the downside of this approach is that it's a lot of extra maintenance, right? There's a lot of components, and a lot of those components were written by people who are no longer actively involved in the project. So, Dave and I basically have to sort of figure out how do these things work and how to fix them. And by and large, they're pretty solid and robust. They don't, they don't break, but occasionally people discover corner cases or problems, or we break them by accident. And the other thing is the system has, as many systems do, has played a kind of dual role. It's on one hand, it's been used in production, it's been used in commercial products, it's been used heavily for teaching, still to this day, but it also was a vehicle for research, right? So Andrew Appel and his students did lots of stuff. Zhang Xiao subsequently at Yale, and his students did lots of stuff. There were people at University of Chicago who've worked on it as part of their thesis research. And so, systems like that accumulate various kinds of barnacles, right? Bits of code that was there to support someone's experiment or someone's PhD, but they're not supported, they may not work anymore, but they're sitting there occupying space and intellectual effort. So these are all sorts of issues that we've had to deal with. So what are we trying to do? Well, first of all, we're trying to streamline and document the existing code, and in part this will hopefully allow the system to continue on maybe 50 or 60 more years after Dave and I are in the ground, so to speak. It will. We've been removing these barnacles, this code that's bit rotted away, doesn't really work, doesn't do anything useful. We've been doing wholesale rewrites of components. Now, this is actually a tradition in the system. I think There isn't anything in the system that really dates back to 1986. Large parts of the system have been rewritten. Some of them rewritten multiple times. We're also trying, as a process of this rewriting and restructuring, we're trying to make the compiler more modular, right? So currently it's very monolithic in its design, but really a modern compiler ought to be structured as modules, not as some big monolith. And once you have it structured as modules, you can then start to use those modules for other activities like building, say, an LSP server. And then also, once we've got this cleaner base, we can start to add new features and components that weren't really plausible to add in the past. So this is the basic agenda of what we've been doing and what we're hoping to continue doing in the future. So I want to give a bit of an overview of how the system is organized, just because otherwise the rest of the talk won't make a lot of sense. So at its heart, there really are three main components. First of all, there's the standard ML compiler and supporting libraries. So this is like the basis library, SML New Jersey library. That's about 225,000 lines of code, not counting comments and white space, et cetera. So just code. And this supports both the interactive and batch compilation, as well as library support for applications. Then there's the compilation manager, which is fairly tightly integrated into the compiler, but is conceptually a separate piece of code. That's about 10,000 lines. That was developed by Matthias Bluma. And then there's the runtime system, which is about 25,000 lines of C code, and maybe another 1,500 lines of assembly code and the assembly code really supports 4 different architecture operating system combinations currently. So that 1,500 lines is not for one machine, but for 4 machines, if you will. Now, at runtime, so when you one of the things, because it's self-supporting, we don't depend on object file formats. So when we compile a module, what you get is, well, I should say when you instantiate a module, what you get is a tuple, which represents the dynamic components of the module, right? The values, the exception definitions, but not the types. And so that means that structures just become functions that take the free components that they depend on and produce a record, and functors are functions that take the free components and then return a function that takes the arguments to the functor, and then that in turn returns the record. So everything is, at this point, everything is just lambda calculus. And since everything is lambda calculus, linking is beta reduction. And so that's very nice. It's completely portable, and we don't have to know anything about object files or anything like that. So standalone executables, to the extent that they exist, are actually built by batch compiling source code into binary files. We have our own sort of minimal representation of binary files. There's no symbol information in these things. This is really just code, and like how much code is in there. Technically there's a little bit of extra information that the bootstrapper needs, but I won't go into that. So you compile to machine code files. We call them bin files. You then load those in. You run the runtime system in Bootstrap by doing all these beta reductions. And at the end, you have a SML function that you can run, and that SML function typically exports the heap image, right? So it's just a snapshot of the current heap. Write that out as a file, and then that's your executable. So to run the executable, you can technically link it with the runtime system, but typically this is done by just dynamically loading. So it's like jar files in Java, right? You just read in the heap image, run the file system, and away you go. And even when I say you statically link, what I really mean is you just embed a copy of the heap image into an executable, and the executable then just reads, rather than reading from the file system, it just reads from its own executable. Okay, so I also want to talk a little bit about the details of the compiler. So it's very conventional, source to source transformations between intermediate representations. So you start with a parser, you get something that we call AST that gets elaborated into absin. Absin is then translated into Flint, which was this intermediate representation developed by Zhang Shao and his students. It's a strongly typed intermediate representation based on F omega. It's actually a very impressive piece of engineering because it scales really well, which is typically not true, or I should say, which is a challenge for very rich intermediate representations that have lots of fancy type features. I won't cast aspersions on other systems. And it models both core language and module level types. Pattern match compilation is embedded as part of this absent to Flint translation. So Flint is used for various high-level optimizations. I think originally the intention was, in fact, to do all optimization at the level of Flint, but that never really fully got fleshed out. I think Stefan Monnier did inlining, but there wasn't a lot. There wasn't the full complement of optimizations. But there are a couple that are really actually important to performance. One of them is a type-based arity raising scheme. This is a little bit like Xavier Loise's idea for using types to do unboxing. There's some space safety issues there you have to worry about. And there's the choice of representations for things like data types and function arguments are also done at that point. That's then turned into CPS, which is continuation passing style. And we throw away most of the type information. We do CPS to CPS transformations, which are our basic low-level optimizations, such as contraction or shrinking, inlining, uncurring. Then we rewrite the CPS into closure passing style, which is also CPS. Nice pun there in terms of the acronyms. And in fact, is also the same intermediate representation, except that the invariants are somewhat different. So there are no higher order functions at that point. And finally, you take this first order closure passing style representation and you turn it into machine code through the ML'23 framework. And so that's that's how the compiler works. Okay, so I've used up 12 minutes and I'm now ready to actually talk about what we're doing. Okay, so in the 2010s, there were a few things that happened. So the first one was we realized that 32-bit systems were not long for the world. And in particular, Dave and I both like to use Macs, and Apple has said, well, at some point in the late 2010s, you're not going to be able to use your 32-bit Mac anymore on the latest operating system. And this also, Linux is basically had dropped mainline support for 32 bits. In addition, the Milton folks were experimenting with successor ML features in their compiler, and we sort of wanted to maintain compatibility with that. Successor ML actually has an implementation that Andreas there did, and on top of Hamlet. So it's not completely a paper design, but it's basically a collection of ideas about how to improve and refine the definition of standard ML. And there is, in fact, a version of the definition of standard ML that has successor ML edits to it that exists. In addition, sort of in parallel to that, we're enhancing the SML basis library so these things were all things that basically motivated us to get started actually working on the system in a serious way again. And so in 2016, so we were around version 110.80 at that time, we started the process of trying to port to 64 bits. This actually turned out to be a lot more work, I think, than we had anticipated. And in particular, it was a lot of work because we had many, many years worth of code that had been written assuming that computers were 32-bit machines. Even code written after the alpha existed and after MIPS was shipping 64-bit processors, people were still saying, oh, computers are 32-bit machines. And those assumptions just completely permeated the intermediate representations and algorithms for various places and stuff. And it was just, it took a long time to sort of root them all out. Once we had sort of generalized in that respect, the actual process of porting 64 bits wasn't so hard. We already had an existing AMD 64 code generator that Mike Rainey, Mike's back there, had written as part of the Manticore project. His compiler, this was part of ML', generated assembly code, but someone else had come along and added machine code, and I'm sorry, I don't remember who it was, but I should give them credit for that, and I just basically had to debug what they had done and get the assembler and stuff working. So it by December of, not 1996, but December of 2019, we basically had a stable 64-bit implementation, and that's really been the default since then. Another thing we worked on about the same time is this, what we call deflintification. So Flint had sort of extended its tentacles throughout the compiler, and we sort of had to chop those back, and that is mostly done now. I think there's one example in the front end that still needs to be removed. Dave rewrote the handling of overloading for operators and literals. This is a kind of ad hoc overloading. We've been, of course, tracking the changes that Milton was making to successor ML. Most of these are basically syntax. They're not really that deep. The one more significant non-syntax thing had to do with OR patterns, but we actually already had support for OR patterns, so we were good. And we also updated the runtime system code to C99 because it basically was ANSI C at that. Yeah.
One more thing is the rewrite of the match compiler, which we talked about last year.
Yes, I will get to that. I anticipated that. That happened later. Okay, so in 2020, we decided to replace the ML' code generator with one based on LLVM. And at the same time, we were running out of version numbers. And this is actually the second time we've run out of version numbers. If you go back long enough in history, there actually was a 0 dot in front of 110. So we got up to like 0.100 and kept going. And eventually when we got up to, I think, 110, and we started iterating like 110.1, 110.2, et cetera, we said, okay, let's drop the 0 dot. So, so that happened back when we were all still at Bell Labs. So we were running out of version numbers, and so we made the decision, which I think is a good decision, which is we split the system into a legacy branch, and those numbers are like 110.99.4 is the latest version there, and a development version. We're currently at 2023.1, where we've switched numbering conventions. We're using year dot release number for that. And the idea here being that people can still use the legacy branch. It still supports 32-bit executables, and we can do whatever we want in the development branch without hurting people. So the development branch does self-compile if you have the right machine, but it's not really ready for production work. So it gives us this kind of a sandbox where we can break things without affecting end users. It is currently the focus of our ongoing and modernization efforts. So, in fact, what have we done so far? Well, we re-implemented the pattern match compiler, and as Dave mentioned, that was talked about last year at the ML workshop. There's this LLVM code generator, and I'll talk a little bit more about that in a moment. That was also described in an IFL 2020 paper. There's a new pretty printing engine, which Dave is going to talk about in the next session. We are working on rewrite of the runtime system with major GC improvements. I'll talk a little bit about that in more detail. And we also migrated to GitHub last year. And that actually turned out to be a lot harder than it should have been, but mostly because of the bug database and turning those into GitHub issues. But it's done. Okay, so I'm going to talk about the code generator. So we use ML'23. ML'23 goes back a long way. We had a paper, Law George and I had a paper in 1994 at the compiler conference about it. Later papers in PLDI about it. And it's effectively allowed us to support native code generation, good quality native code generation for a lot of different architectures for many years. I mean, in the history of standard ML, we've supported 10 different architectures using that framework. We currently don't support all of those. Many of them don't exist anymore, but you know, like VAX, for example. It's a very nice design from many respects. It's a mechanism, not policy design, and that's really great if you're trying to do non-standard runtime system models, because it doesn't bake in a lot of assumptions about, oh, you have a stack, oh, you have this calling convention, et cetera. It's all, you roll your own. But it's not actively maintained. I mean, Mike really is the last person to do a substantial addition to it, and that happened in the, I don't know, around 2008 maybe. So, it has some bugs, and so we wanted an alternative, preferably one that someone else was maintaining. And the obvious choice, of course, in the modern space is LLVM. That is the, you know, sort of the big, mature, widely supported system. So we had some goals and some challenges. So we wanted to preserve our existing runtime model, and our runtime model is based on this idea of heap allocated return continuations. So there's no stack. All things get passed in registers. We wanted to maintain the interactivity of the existing code generator. So you would type stuff at the terminal and it would come back immediately, and you wouldn't have to wait a long time. We needed to be able to generate raw machine code in a format that is compatible with our runtime system. We wanted to keep the C++ code as sort of simple as possible. So we didn't want to be writing a lot of C++ compiler code. We wanted to be writing SML code that compiled stuff. And lastly, I mean, for people familiar with with LLVM, all of these things are actually hard to do in LLVM. I don't really have time to explain why, but you can ask me after. But LLVM has a really heavy bias towards C and C++-like languages. It is designed to support compilers that use that runtime model, and that makes it a challenge for people who are doing something very different. So, how did we do this? Well, we used this thing called jump with arguments, which we developed. One of my students and I developed for Manticore, which was this parallel ML compiler we were working on in the 10 years or so ago. And we added an extra low-level IR to that's more explicit than the first-order CPS that we had. And we use ASDL, which was a tool that was developed many years ago to allow compiler components to talk to each other. There are, you know, compiler components written in different languages to talk to each other. So we serialize the intermediate representation, pass it into the runtime system, and the runtime system uses that, deserializes it, and uses it for code generation. So we have a code generator now that sits on top of this LLVM C++ API. Currently, we have backends that support x86, 64, and ARM 64, but there's some serious bugs. So it works in some limited situations. It works well enough to self-support, but it's not really ready for prime time yet. And again, there are details in this IFL paper. Just quick performance numbers, because I know I'm starting to run out of time. So it slows the compiler down, sometimes by a lot. I think the worst, well, these are really small examples, but like if you compile the compiler, it takes 3 times longer using the LLVM backend than the straight backend. But it's not too, it's only a little bit over 2 minutes, so it's not so bad that it's going to really be terrible. And we have very good incremental recompilation support. So as long as you don't need to compile the whole compiler, it's not so bad. On the other hand, things actually get faster. Typically, I think sort of roughly 15 to 20% is probably a good guess for performance improvement. So we are picking up some benefits from that. And of course, we get the portability benefit, which is perhaps the most important thing. Okay, so I have 5 minutes, I think. My clock says 5 minutes, so. All right, so another major thing that's sort of currently work in progress is a rewrite of the runtime system. And LLVM, the code, and we stripped out a lot of code from this source tree, but we still have 1.6 million lines of C++ code attached to our small 25,000 line runtime system, right? So the C++ code just completely dominates. Now, it's also the case that modern versions of C, and by modern I mean versions that are 20 years old, are not actually supported on Windows. Windows kind of stopped with ANSI C, basically. Some features are, but not the full language. And it was also the case that we actually had sitting around a version of the runtime system that was written in C++ in the mid-2000s. And so, for these reasons, decided to basically sit down and rewrite the system, but using modern C++. So in the C++ community, anything after C++ 11 is called modern. And specifically, we're using C++ 17 because that's the current standard that LLVM is using. So why do we want to do this? Well, one thing is we can actually take take advantage of templates that reduces the code size. So the C++ code is actually about 10% smaller in terms of source lines than the C code. We also can make some parts of the system more type safe, in particular the interaction between the runtime system and SML. So let me just briefly talk about that. So we introduced C++ classes that represent SML types. So for example, string value is a SML string, and we can use templates like list type here as essentially the list type constructor from SML, but as a C++ template. So you can have like a list of strings. And so here's an example. This is from the old runtime system. And in the old runtime system, we basically use these macros here to sort of convert between between the SML representations and C representations. And hidden in this is actually a conversion back the other way, along with some error checking. So when we write that in C++, we now just basically write down a type. So here we're saying this thing is a triple. It's the first thing is a value, because we put all the integer types just become values. We don't have specific classes for those. And it's a vector of bytes and another integer. And we then can just use our just extract those values directly in a somewhat more type-checked way. And the nice thing here, though we don't currently exploit it, is, two nice things. One is this code can actually do runtime checks to make sure that the argument is actually plausibly a triple, and of the appropriate types. And the other thing is, this thing and this comment are actually not, reflect the same information, and so there's actually potentially an opportunity there to be machine checking the interfaces. Okay, so I'm almost out of time, so I'm going to skip talking about garbage collection. So I'll just skip the garbage collection because that was. I'll just talk about future plans, and that's the last slide. So, okay, so what do we want to do in the future? Well, first, we'd like to sort of continue to use ASTL. There's a pickler in the system that's a handwritten thing that's a very difficult thing to update, so we would like to replace that. We have plans for rewriting type checker and module system with better error reporting. This is also part of the sort of making the compiler more modular. So we'd like to take these, we'd like to have the compiler be a bunch of libraries, and then we can have the REPL be a program, we can have the batch compiler be a program. Someone can put together an LSP server as a different program, but these things will be built on a set of common libraries, and so I think that will be a much better architecture. A lot of these things are just rewriting things that need to be rewritten, so rewriting the compilation manager, and we'd like to extend the compilation manager with MLB support, which is the system that the SML kit compiler uses and the Milton compiler uses. We would like to continue adding successor ML features. We did a paper in 2019 at the ML workshop about how to do the guard pattern, or pattern guards, I guess they're called. I've got a student who's working on rewriting the safer space closure conversion algorithm, but to use actual higher order control flow analysis information rather than the very limited information we currently use. We wanted to replace our current very hacked up installation system with something maybe based on CMake. And I was inspired by Andreas's keynote to realize that, in fact, particularly if we modularize the compiler, it should be very easy to build a WASM backend, because once you get down to the first order representation we currently are using, I think the gap from that to WASM is actually going to be very small. So that is my talk, and I apologize for running over time.
So when you go through all the effort of rewriting the runtime system, like the hype of current days is using Rust, right? Was that a consideration at all?
So I guess I thought about it, and I would say there are two reasons why I didn't do that. One is a large motivation to do this is basically build compatibility with LLVM, because LLVM is clearly going to be, is going to be the dominant piece of source code in the runtime system. And so using the same language as LLVM is written and is nice. We won't have to, there won't have to be any kind of shim. I assume there probably is a Rust wrapper for LLVM, but then you're dependent on a wrapper, which is dependent, so when LLVM changes, now we have to wait for the Rust people to update their wrapper, and then we can update our code, so I think it introduces a lot, sort of more moving targets, I guess is one way to say it. And I don't know, I know Rust in a sort of scholarly academic, I've seen a lot of talks on it way, but I haven't really written any serious code in it, so. Where is it?
Thank you.
Thank you.